Today we are going to see Moore machine. What is Moore machine? It is a machine in the theory of computation which produces output and output, or I can say finite automata with the output, but output is associated with the states. So in the definition, we can say Moore machine is defined as a machine in the theory of computation whose output values are determined only by the current state. So how to define it? It is a six tuple, capital Q, Q0, alphabet set sigma, capital O output set, this is transition function delta and lambda. So capital Q is a set of finite state, right? It is a finite. Q0 initial state. This is input alphabet set. This is output alphabet set. Lambda is output function at a particular state. What is output? See, output is related with the we can say only the state, not with the output input what you are reading. Okay, so and we can say, see, this is important point to note down. Output is associated with the state, not with the input, whereas transition function what is a new state. For that you should know current state and the current input that you read. So let's see how Moore machine looks like. So here this is one example. Don't bother about what is a problem statement and this is drawn for what problem statement. We'll see this is how it looks. I just wanted to show you these are the states as per the definition whatever we have seen right now. The output, see how many states are there? A, B, C, D. What are the output? X1, X2, X1, X2, X3. Three outputs are associated with the four states. Fine. Out of 2, X2, X2 are associated with the A and C. Right. So this is how it is written. Earlier, we know that in the finite automata, only we are writing here state name. Q0, A, B, C, whatever it is. Here states are A, B, C, D. Along with that, /x2, here x1. Why it is written? Because this is a Moore machine representation, right? And our output is associated with the state. Why? This is one way to write name of the state / output associated with this. Alternatively, you can write as well below here. X2, you can state name is here. Below that, we can write the output associated. Alternative way to represent the Moore machine. Now here see, if you observe that as per the definition, transition function, particular state, reading input symbol, what is the state? So in this matrix, present state, what is the next state? On reading the input, this much part give, this much part talk about the I can say transition function, that is delta. Okay, what is the delta transition function and what is the current state and current input? Now only present state and its output, these two things give me the capital O, that means output function. Is it clear? Or sometime O can be represented as like this. Sometimes this symbol also can be used, few books uses capital O, few book uses this delta function again to represent the output function. So depending, just don't get confused in the symbols. Very first dimension, which symbol represent, or what is the significance of that symbol, go through it once before reading that particular reference book. Yeah, so here this two things gives me the output function and this is the transition function. And see here at a state A, output associated with x2, that's why it is written here. I use another pen to show you. See, x2. How I come to know? From this matrix. x2 is associated with the A, x1 is associated with the B. This is represented from the graph, right? If I know the matrix, I can generate the graph. If I know the graph, I can generate the matrix. Now, how to design our own Moore machine? Let's see one example. Construct a machine to find out the residue modulo 3 for a binary number. So binary number, we need to define, we have to solve by using this definition. What is a capital Q? How many states are required to solve that problem? What will be the initial state, input set, output states, output set, what are the output symbols, transition, and the output function. So for this, how many states are required? It is to find out the residue modulo 3. So output will, if you divide any number by 3, you will get 3 remainders. It may be 0, 1, 2. So these are the 3 outputs. If you, right? So, and binary number, we are using binary number. So my input alphabet set sigma is 0 and 1. And what are the states required? Now 3 outputs. So 3 states are required as we are talking about the Moore machine. Fine. So I will, if my remainder is 0, I will call that state as I am in the state Q0. If I got remainder 1, I will go to the Q1 state. 2 is the remainder. Then I will go to the Q2 state. This is for sake of understanding. 0, 1, 2 are nothing but the output associated with this state. Right. So now first machine function. This is what machine function we have drawn for Q0, 0, right? And now state transition. These many states, Q0, Q1, Q2. Out of that, which one is the initial state? Here, initial state is Q0 because we are starting with the A state 0. The remainder is 0, assuming that our remainder is 0. So, we are in the state Q0. This is our initial state. And then we are moving from state to state on reading some input symbol. So, now here, suppose I see first 0 in the Q0. So, I will be in the Q0. I will not go to the next state. Now, if I get 1, so assume that, remember that thing, we are using the input alphabet set. Now my alphabet set is here, wait. My input alphabet set is here 0 and 1. Right. So on reading 0, what will be the next state? Here we have mentioned, if I am at the state 0 and read 0, we are talking about binary number, right? So how to represent 1 in the binary? It is 0, 1. Assuming that initially there was nothing present on the 0 state, right? So if I saw 1, so divide by 3, I will get the remainder. How much remainder will be there? 1 divided by 3. Again, it is remainder 1. So on reading 1, I will go to the state Q1. Right? So initially nothing will be there. So 0 divided by 3 decimal. If you do that in the decimal, so your remainder is the 0. So you will in the state Q0. On 1 divided by 3, remainder will be 3. Remainder will be 1. So I will be in the state. Right now, whatever we discussed about the states, right? If I'm in the state 1, now I read 0, 1. Now I'm in the state 1. So earlier, what was my input? 0, 1 was my input, right? And on that, I get now either 0 or 1. So this is what my value. 1. So, see, at a particular state Q1, this is what your initial state. You have read string 0 1. Now you will get 0 again. So this value is 2, right? 2 divided by 3. So how much the remainder? Again 2. So on reading 0, you are going to state Q2 because output associated with the state is 2, right? At a state Q1, still that you will have you have read this 0 1, and after reading that you will get 1. So this becomes 3 divided by 3. Remainder will be the 0. So at a particular state Q here in the Q1, if you read 1, so you will go back to the Q0, right? And again similarly Q2, for the Q2 you have read 1 1, sorry 1 0. Now after 1 0 you may read 0, you may read 1, right? So 1 0, after reading 1 0, input may be you are in the state which one? Q2. So in the Q2 you may read 0 or you may read 1. So now this is the binary 1 0 0 means decimal 4. So 4 divided by 3. What is the output? This what is the remainder? Remainder will be 1. So in the Q2 state, on reading 0, you will be in the Q1. Similarly, after reading 1 0, you are in the state Q2. So after Q2, if you read, that means already you have remainder 2. 2, on that 2 you will get 1 more. So in the you can convert into the decimal. So this is 5. 5 divided by 3. What is the remainder? 2. So on reading 1, you will be in the same state. So this is how to draw the diagram. And one more thing here. Remember earlier what we have seen here, output is written in the state, right? Oblique x2. Now here what we have written, we haven't written q0 oblique 0. That is one way to write, or you can write like this. Below state name, I have written the whatever the outputs associated with the states are written. Fine. This is another way you can write like this. In the state only Q0 slash 0. This is also can be written. Or another way to write, output associated can be written below the statement. These are the two alternatives. Fine. I hope you understood this part. Now see, what is the difference between the Moore machine and the Mealy machine? Output depends only on the current state. Right now we have seen Mealy machine output depends on the present state as well as the present input. If we changes the output, if input changes, does it affect? Because input is not related with, doesn't bother in the Moore machine, so output does not change. But in the Mealy machine, as it is related with, it depends upon the input, it will change output as well. More number of states are required in the Moore machine. Why? As we know that output is associated with the state. That means that however, how many outputs are there, that many minimum states are required. Earlier example, we have seen same output can be related with the multiple states. So from that we you understood. I think you understood that more number of states are required in the Moore machine, whereas less number of states are required in the Mealy machine. Obviously, but hardware thing, less hardware is required for the circuit implementation by using the Moore machine, whereas Mealy machine hardware is quite complicated, or it required more hardware. As hardware, we can say more hardware is required, so designing is more complex in the Mealy machine, whereas Moore machine, it is easy to design. And very important point, synchronous output and the state generation. Here we have to synchronize because output is related with the states. So synchronous between the output and state is must in the Moore machine, whereas it is not required in the Mealy machine. And output is placed on the state, output is placed on the transition in the Moore machine. I hope you understand it. Thank you. The references